Hello guys, so welcome back to our lectures. So in this week, we're going to continue our discussion about the design and the analysis of synchronous circuits, okay? And that's basically very important topic. So we're going to continue examples and we're going to do the up-down counter again, but now using JK flip-flop. And the reason is because it's trickier than using D or T flip-flop, okay? And you know that trick in JK, if you did it right, you will get the optimal design. Otherwise, your design will be correct, but it might not be optimal. Okay, so same specs. Okay, everything is the same, just like the D flip flop example of up down counter, but now using JK. I mean, we're gonna use Moore circuit in which the output is only dependent on the state, not the input X. We have again 1-bit input to determine the either count up or count down. And again, when we're gonna choose that when X is 0, we're gonna count up. When X is 1, we're gonna count down. And since we have 4 states, you have 2 flip flops. But now these flip flops are JK flip flop, not D flip flops. In the homework, it's a T. Okay, so now you explored everything. So let's see what will be the change. Of course, so the first steps of the design will be the same. Although we're gonna just use JK flip flop, not D flip flop. Now, how about the state table? State number 3. After deducing or driving the state diagram, we go to state table and we fill the state table based on the state diagram. Okay, so the change here is that instead of DA and DB, we're gonna have GA, KA, which are the inputs of the first flip flop, because JK flip flop has 2 inputs. It's not one input like D flip flop or T flip flop. And the second flip flop will have JB and KB, not just DB like the D flip flop. It has 2 inputs, not just one. Okay. And here is the trick, because it's not that simple like D or even T. Okay. And we must here refresh our memory with the characteristic table or the state table of the JK flip flop. So in the JK flip flop, you have 2 inputs for the JK, which basically G and K. Okay, and based on that 2 inputs, we're gonna determine Q of T plus 1 or Q plus. Again, we said that last time. I'm gonna use Q plus here to represent Q of T plus 1, the next state of the output of the flip flop, and the current state is just Q, which is basically Q of T. Okay, so JK has have 4 combinations: 0, 0, 0, 1, 1, 0, and 1, 1. Okay. What will happen if JK is, both are zeros and the clock edge come to the flip flop? Okay. So we said that this is a memory state. Memory. Which means Q plus will be equal to Q, or Q of T plus 1 will be equal to Q. Or you can say the output of the flip flop will not change. If there was a 0 before the clock edge, it will be still 0 after the clock edge. It will not change. It's a memory state. So Q plus will be equal to Q. Memory. No change. Good. If J is 0 and the K is 1, we said, when we explained the JK flip flop, this is a reset state. Reset means whatever the current Q is, whatever Q of T or whatever Q plus will be 0. Reset. Reset the output. Make it 0. Now, when J is 1 and the K is 0, this is a set state. Set means Q plus will be 1, whatever Q of T or whatever Q. Finally, when J and the K both are 1s, we said that this was forbidden state in RS. Now, here it's not a forbidden, and that's why JK is good to use, not like the RS. Okay, and this is basically a toggle state. Toggle. Toggle means a complement. You can say complement state as well. You know, whatever you like, just naming. Toggle means here if Q is 0, Q of t is 0, Q of t plus 1 will be its complement. It will be 1. If Q or Q of t is 1, Q plus or Q of t plus 1 will be 0, just as a complement. So here Q plus will be just Q complement. Toggle, you know, change in the state. It's change in its value, basically, 0 to 1 or 1 to 0. Okay, so you know, we're gonna look, you know, back and forth to that state table of the JK flip-flop when we do that, you know, when we fill basically the 4 columns now, GA, KA, JB, KB. Let's start by GA and KA, or basically QA and QA plus. Okay, so in the beginning, we have 0, 0. QA is 0, QA plus is 0. Okay, let's write this on a side here. QA 0, QA plus is also 0. Oh, that, you know, so you can interpret or translate such a state here in 2 ways, and that's the trick of JK flip-flop basically. So QA plus is 0, right? You might say it's a reset, right? So you might say that's a reset state. Or you can say that that means that JA basically is 0 and the KA was 1. Then when the clock edge come, we reset the output and the output becomes 0. Of course, it will become 0 regardless of the previous output, regardless of Q. Q plus will be 0 regardless of Q. And it happens here that Q is 0 also. So it's not a change, no change, right? So you can interpret also this Q 0 and Q plus 0 as no change. That's another interpretation, no change, or memory state, which means GA is 0 and KA is 0. I know now you are confused, but let's you know, repeat it a little bit in that way. Look, if you have J equal to K equal to 0, and the Q was 0, and the clock edge comes, what will happen? No change, right? Because J and K are zeros. So Q plus will be 0. Good. Now, if you have J is equal to 0, K is equal to 1, and the Q is equal to 0, then the clock edge comes. What will happen? Here you say that J is 0 and K is 1. This is a reset state. So Q plus will be 0 regardless of the previous Q, regardless of Q of t, right? So Q plus will be 0. So look, Q0, Q plus 0 can happen with 2 combinations of JK, either 0, 0 or 0, 1. Okay, that's why it's a trick. So let's do that here on, you know, on a side here with you know, in the bottom of this table here. When Q 0 or Q equal to Q plus equal to 0, whatever you like. This can happen with 2 cases for J and K. So either 0, 1, and always J before K, or 0, 0. So look here, J in both cases are 0, right? But K can be 1 or 0, right? It's a don't care. So that will be interpreted to 0x. Okay, so whenever you see Q and the Q plus both are zeros, then you're gonna put for JK 0x. 0x. One may say, what if I put it 0, 1 or 0, 0? Does the design is will give incorrect result. No, my friend, it will still be correct, but it's not guaranteed to be optimal. Why? Because remember, the next step after putting or filling the state table, we're gonna do the Carnot map to get GA, KA, GB, KB. And the more the don't cares you have in your Carnot map, the more the wine groups can be, formed. So the less literals you will have in your final equations, the less literals mean less hardware or less complexity. So more optimality, right? So that's basically why this will lead to optimal design. If you use 0, 0, I mean J is 0. So if you here I put 0x, if you put 0, 0 or 0, 1, still correct, but not guaranteed to be optimal. Of course, you might be lucky, but it's not guaranteed. So whenever we see 0, 0, we're gonna put 0x. Good. Next, state. Let's erase here this. Next, state here, or next, enter in the table QA 0, QA plus 1. QA 0, QA plus is 1. Again, here you can interpret or translate this in two ways. QA plus is 1. You might say it's a set state, right? You might say it's a set. Set means that GA was 1 and the KA was 0 when the clock edge comes. That's why QA is 1. Another guy here say, no, it's a toggle state because Q is 0 and Q plus is 1. It's a complement, right? Q has changed from, it's the complement of its last value. Okay, so Q of t plus 1 equal to Q of t complement. So you might say, no, it's a toggle state, and GA was equal to KA. Basically, both are 1s, and actually both are correct. Both are correct. Let's do the example again. Look, if J equal to 1, K equal to 1, and the Q is equal to 0, then the clock edge comes. What will happen? J and K are 1s. This is a toggle state. So Q plus will be the complement of Q, whatever it is. So the Q is 0, so the complement will be 1. So Q plus is 1. Good. If J is 1 and the K is 0, and the Q was 0, and the clock edge comes, oh, this is a reset. So whatever Q is, Q plus will be 1. Look, both lead to the same conclusion. Okay, either J equal to 1 and the K equal to 1, or J equal to 1 and the K equal to 0. Both were Q equal to 0. This will lead to Q plus equal to 1. And that's our next or second rule here, that when Q is 0 and Q plus is 1, this might happen with 1, 1, G1 and K1, or 1, 0. So again, J is constant equal to 1 and the K can be anything. So we're going to put this as 1x. So here 1x. One may say, no, I will put it 1, 1. Okay, my friend, put it 1, 1, but your design might not be optimal. But it's correct. The functionality is correct. I mean, at the end, it will be up-down counter. Don't worry about that. But you might use, extra hardware, extra gates, for example. So this is rule 1. This is rule 2. What I mean by rule 1 and rule 2? Rule 1 says, whenever you see Q and Q plus equal to 0, put 0x. Rule 2 says, whenever you see Q0 and Q plus 1, put 1x. The third row, 1, 1. QA1, QA plus 1. QA1, QA plus 1. Let's see. One may say Q plus and the Q are the same. So it's a memory, right? And that's right. That's a memory. Memory means J equal, so JA equal to KA equal to 0 or 0, 0. One might also say it's a set state because QA is 1, right? So you might say it's a set. And J, set means J is equal to 1 and the K is equal to 0. And again, both the same, example. Assume J is equal to 0, K is equal to 0, Q is equal to 1. When the clock edge come, it's a memory. So same Q will be coupled to Q plus. When J is 1, K is 0, and the Q is 1, clock edge comes. This is a set. Whatever Q is, Q plus will be 1. Third rule. Let's put now the third rule. Number 3 here. Q is 1, Q plus is 1. This might happen when 0, 0 or 1, 0. Look now. Here, K is constant and J can be anything. So that's basically X 0. So this is X 0. Rule 3. Whenever you see Q1 and the Q plus 1, this is X 0. Okay? Let's do now the fourth column or fourth entry, fourth row. 1, 0. We didn't do that before. So 1, 0. So 1, 0. So QA is 1. QB, I'm sorry, QA plus. There is no here. Control Z. QA plus is 0. It's a toggle. This is just like this one, exactly like it. Okay, it's a toggle or reset. So this is might be toggle or reset. Let's interpret that in our fourth now, and actually the last. We will not do any more rules. We're gonna find ourselves, using these rules from now on. When Q is 1 and the QA plus of Q, just make it, general. Q plus equal to 0. That might be a toggle, which means 1, 1. Or reset. Reset means J is 0, K is 1. And look, K is constant, J changing. So whatever J is, whenever K is 1, that's will give you 1, 0. If Q is 1, this will give you 0. So that's basically X1. X1. From now on, we're just gonna look at this. We don't need to analyze anymore. We're gonna just look at the 4 rules and apply and fill the table. Let's check. So the fifth column, fifth row here, 0, 1. We did the 0, 1 before. It was 1x. Very nice. 0, 0. We did the 0, 0 before. It's the first row here. It's 0x. 0, 1, 0. We did the 1, 0 before. It's x1. Finally, 1, 1. We did the 1, 1 here. It was x0. Now, we're going to do QB plus, and of course, fill JB column and KB column. And again, we just look at the 4 rules. That's it. Okay. Let's change the color. Make it, for example, green or whatever. Okay. 0, 1. Where is 0, 1 here? Yeah, this one, rule 2. 0, 1, you have 1x. Second row, 1, 0. 1, 0 is Z1 here, x1. 0, 1, again 1x. Then 1, 0, again x1. Then 0, 1. Where is 0, 1? Again 1x. Yeah, this I know with the solution here. It will be toggling between rule 2 and rule 4. Okay. Then 1, 0, again x1. 0, 1 again, so 1x. Then finally 1, 0, it's x1. Okay, yeah. QB and JB and KB, we just gonna toggle between rule 2 and rule 4. Okay, that's basically the nature of the problem. It's a coincidence. Okay, guys, that's the state table. What we do after the state table, if we refresh our memory with the design, problems, we do the Carnot map to get the two outputs. Let's change the color. The two outputs and the input of the flip-flops, which is basically 4 now. They are not just 1 for each flip-flop. No, it's 4. Each flip-flop has 2 inputs. So you should have 6 Carnot maps here. 6, but luckily we know that YA is equal to QA. This is from the from the last lecture. So when we did this, solve this this problem or this design using D flip-flop, we knew that YA all the time equal to QA and YB is equal all the time to QB. Okay, so you're just gonna save 2 Carnot maps now. Now you just do 4 for JA, KA, JB, KB. So let's do this. Okay, so here is the 4 Carnot maps. Okay, let's do just one of them to refresh our minds. So let's, for example, do GA here, 0, 1, XX. So 0, 1, XX. And then we have 1, 0, 1, 0, XX again. So it's exactly what we have, and the rest, of course, is the same. This is, correct solution. So let's group here. So this one here has it has 2 adjacent zeros, this 0 and this 0, but it has X here. So you can consider this X as 1 and make a group. This group here. That one here has also 2 zeros as neighbors, and this neighbor, remember, the Carnot map is rounded, is X, so you can consider it as 1. So you have another group here. So that will give us the following: the GA equal to. So this group in the top here, it is basically X bar QB, X bar QB plus, and that group here is basically X Q bar, X and Q bar, because this is Q bar, this is also Q bar, and you know that this is XOR, right? X Y bar plus Y bar X, this is basically XOR. So GA is QB XOR X, or X XOR QB, whatever you like. Okay, now let's do KA, because surprisingly it will lead to the same equations. Okay, so XX01, XX01. Okay, then XX10, XX10. So again, this one here has 2 adjacent zeros, but this X here can be considered 1. So you have here a group. This guy again has 2 zeros, but this can be considered 1. This X here. So here you have another group. So this will be, X Q bar plus X bar QB. So basically the same, right? So again, KA is equal to QB XOR, or equal to GA, they are equal to each other. JB KB, this is really, really nice. The XOR here, make a great, advantage for us. Look, if you consider all the XORs are 1, then this is just one group, and GB will be just 1. Very optimal. There is no optimality, rather. This is, the final, optimality form, that JB or whatever the variable is equal to constant. There is no gates at all here. You just, in a real circuit, you just connect this input to the VCC, the highest voltage in the circuit. That's it. And for Kiwi, the same. Again, you can consider the X's here, don't cares, as ones, then Kiwi will be 1. Just one group, and Kiwi will be constant equal to 1. So we found that GB is equal to KA is equal to GA, and GB is equal to KB. Okay, so let's now do the the implementation. So here is the 2 flip-flops, JK flip-flop A and JK flip-flop B, and we learned it from the the last slide that J is equal to K is equal to X XOR with QB. Here is QB. This is basically X XOR QB. And we learned that JB and KB are just constant equal to 1. Okay, that's basically the design. Okay, again, if you didn't consider this don't care that appears to us, okay, in the state table, you're gonna get a correct design working, that makes up-down counting, but it might not be optimal. Okay, you see here it's really really optimal and it's simple. Okay, guys, that was basically the up-down counter. So stay tuned for our next video also on the design and analysis of synchronous circuits. Thank you very much. Bye-bye.